Welcome to the Wheel of Fortune. We're going to see a whole slew of reactions here, and we are going to work at it group by group. We had nucleophiles, good nucleophiles. We had nucleophiles that could be bases. We had bases that are very strong bases. And then we had protic solvents, weak base, weak nucleophiles. Let's see what happens. Let's spin it. All right, let's start with the first one. That's PPH3. What on earth is PPH3? It's phosphorus nucleophile. You know, when you go down the periodic table, size increases and electronegativity decreases, and that makes it an ideal nucleophile. So bigger and polarizable nucleophile. When we have a nucleophile, we want to be able to put those electrons, squeeze them, and push that iodine or the leaving group out. So the bigger and softer you are, so the ones that are below on the periodic table, like sulfurs and iodides, selenium, phosphorus, these are bigger, less electronegative, and they're polarizable. They can squeeze their electrons and make that sigma bond. So we're going to do that for A. Let's start. All right, so here's our spin, PPH3. So PPH3 is a good nucleophile. It's not a base. It's not going to go after any hydrogens out there. It's just going to go backside attack, kick that thing out, and iodide falls off. So that's one of the first things you're going to do. So I'm just going to put a generic reaction here for all of these nucleophiles. They're going to give a kick on the back and break that bond and send that leaving group on its way. So that's what's going to happen. And you know this is concerted, has a transition state. It's two molecules having to come together to do this. So it's bimolecular, and you know the rest, it's SN2. So all of this, basically, if you with A group, would be mostly SN2, backside attack. So here's your nucleophile, and that's your nucleophile. And in this case, you are going to have your PPH3, then replace, which is what we call substitute, the iodide. So your phosphorus doesn't have a hydrogen to deprotonate to make it neutral, so it's going to be stuck as a positive. The lone pair becomes that sigma bond. The iodide then is going to be a counter ion. That's the product. It's an ionic product. You can precipitate it out. And then you could do, you know, Wittig's reaction if you have oxygens and so on, and we'll talk about that later. This is just a preliminary step to that. Here's our next really nice, beautiful, polarizable nucleophile, sulfur. Large and less electronegative, same thing. So when you have a metal and a non-metal, you know it's ionic. And if it's ionic, it's going to have to dissociate. So a lot of these may not dissolve in all of the solvents out there because they're ionic, and you know ionic dissolves best in water. But protic solvents aren't really very good for SN2 because they tend to ionize them, ionize the starting material. So therefore, you want to find a solvent that would dissolve it. And if you cannot find a solvent that would dissolve it well, then you may have to resort to a protic solvent. So some of the SN2 reactions, even though we keep telling you, oh, it's going to be really fast in aprotic and you should use aprotic, for sometimes for solubility reasons or for even, you know, economic reasons, because you can't really afford such expensive solvents, we sometimes tend to use protic. But if you have a very powerful, good nucleophile, even with a solvent like methanol, you're still going to get SN2. So this is going to kick it in the back, and you are going to get SH. replacing that, and that's why we call it a substitution. And so you have your iodide come out with your sodium, so you'll have sodium iodide fall out. And if you have a solvent that doesn't dissolve the sodium iodide, that would be good, because then you won't have a reverse reaction. So the more aprotic the solvent, the more it's going to go faster in this direction and irreversibly. Let's look at the next one. Same concept. So whenever you see a metal and a non-metal, draw a line and cut the metal from the non-metal. And that would be for all of them, whether it's going to be a base or a nucleophile. So make sure you draw a line between the metal and the non-metal. Here's sodium. So you draw it here. I actually had a student who cut the sodium in two and made nitrogen. So let's not go anywhere there. So sodium over here. Okay. So we're going to cut all of our metals from our non-metals. All right. So let's go. So then what do we do with the metals? Just ignore them. Just take this part, and you know the metal here, sodium, so it has to have a +1. So then you know this is going to be minus. Okay. So you have to really make sure that you know what is the substrate, what is the reagent, and what is the solvent. Don't confuse the solvent for the reagent and try to do a reaction with, let's say, with acetonitrile, okay, so, or DMSO. So make sure that you know which one is which. If you see a metal, non-metal, chop it in two and take the non-metal part, that's your nucleophile, run with that. So just take the non-metal part and replace the leaving group. So basically that's what you're going to be doing for all of them. So here's your selenium CH3. So that's your nucleophile. It's going to attack, kick out your leaving group, SeCH3. And then of course you're going to have your sodium iodide precipitate out. I'm not going to write this out for all of them, but that's what happens. And here's your next one. Cyanide goes in, kicks it in the back. The negative, that is the lone pair, and that becomes the sigma. And then you have your cyanide. And same here with your thiocyanide. And thiocyanide is something that has got a sulfur and a SN. Sometimes they use that in airplanes and stuff. All right, so here is your N3. So your potassiums and your sodiums, they just spectators. They just bought tickets to watch the game. The anion is the one that does all the work. So your anion goes in, and the anion, the fact that it's got an anion means you have a lone pair that's going to kick in and drive out the leaving group. And so here is your nitrogen, and well, there's 3 of them. And then there'll be some resonance going on. All right, so here you'll have potassium iodide fall off. Here's your sodium bromide. It's going to, again, do the same thing. Chop it right after the metal. Take the anion, run with that, attack. And here you'd have bromide. So, and your sodium iodide falls off. Now, if you do this in acetone, sodium iodide will be soluble in acetone. Sodium bromide is not soluble in acetone, and it might go in the reverse direction. So you don't really want to do that in acetone. But if you want to do the reverse reaction where you have a bromide and you want to attack with iodide, then you should probably do it in acetone. Sodium nitrate, same story. I'm just putting this out here just to give you like an idea. I'm sure by now you kind of get the trend. So your negative charge goes in. The negative charge is your lone pair on oxygen, kicks in, makes a sigma bond, kicks that out. Remember, there are 2 hydrogens here, so it's achiral. And here you're going to attack with your oxygen, and then you'll have your NO. Let's look at your sodium acetate. Sodium acetate, well, in Gen Chem, you learned it was a weak base. The weak base can be, can do an E2 or an SN2. If it is a primary, it just does a backside attack and gives you majority or major SN2. And this is your acetate. This is called OAC, acyl group, and oxygen. KH and Me, again, these, I grouped them together because they could do E2 if, let's say, you have a tertiary, okay? But here you have a primary, so these would do SN2 more than E2. So I'm going to write that down here. SN2 more than E2 on primary. This also does the same thing, attacks and displaces the iodine and gives you a NHMe. Now you want to have an excess of this, if you don't want to have this happening over and over again. Here's your satellite. Same thing, your satellite has got a pair of electrons here on that carbon that are non-bonded. So it's an anion. And the anion kicks in, makes a sigma, and kicks out your iodine. So you would have a carbon with a triple bond. And here you could have hydrogen or R group or whatever it is. It really doesn't matter as long as one of the sides is an anion. All right, so those are good nucleophiles. Good nucleophiles do SN2 with primary. In some cases, SN2 over E2. All right, let's move on. So we're going to go over here to our other class where you have bases that can be nucleophiles or nucleophiles that can be basic. Typically, the pKa should be more than 11 for the protonated form of the nucleophile or base. Let's look at these. Water, about 15.7. This is about 16, 17 pKa. So they're very basic. The anions are basic. Now, they would come in protic solvents. And so you might think, oh, well, we have all these protic solvents. What about SN1 and E1? Well, again, if you look at the structure here, water would have 2 lone pairs. Whereas if you take potassium hydroxide, it's ionic. So you cut it up here. And this is going to be a negative because it's got 3 lone pairs. So it's like arm wrestling a guy with 3 hands versus 2 hands. This guy's going to win. So whenever you have a good, strong base or a nucleophile in the presence of a protic, go with the anion. So your anion is going to go in, creep in, kick out the leaving group, and attach here to give you a nice alcohol. And of course, potassium iodide is going to fall out of the solution. Now, potassium iodide in this case is soluble, so you would have it around. But to take potassium iodide and go in the reverse direction would be impossible because OH is not a good leaving group. You know, the OH, the leaving group ability depends on the pKa. The pKa for this is really high, like 16 or 17. You got to be less, you got to be like close to 0 pKa to be a good leaving group. So therefore, this is never going to leave. So the reverse reaction doesn't happen where the iodide comes in and kicks out the hydroxyl, never. And it's the same story with all of them. So same thing. Take your pen and cut up your reagent, metal, non-metal, forget about the metal. Just run with the non-metal because that's where your charge is. That's where your muscles are. That's your strength. You go in, give it a good kick, push the guy over. You kind of a push over basically. And you're going to get a replacement, which is what we call substitution, all happening at the same time. Nice SN2. And here too you have methanol and you have a sodium iodide and it's going to be soluble. Again, it's to do with the lattice energy, why sodium iodide is soluble and sodium chloride, for example, is insoluble. So therefore here this will be soluble, but OCH3, that's never going to be a leaving group. So you have no fear of having a reverse reaction here. When the pK is high, then it's only going to act as a base or a nucleophile and never as a leaving group. All right, let's look at this same story, guys. I mean, there's absolutely no difference here between these two. They're both alcohols, and it could be any alcohol. I mean, I will just put, ethanol, propanol, whatever. It doesn't really matter how many carbons you have or how big it is even. Get a kick in the back, and you're going to have your alcohol then come over. Same story as before, sodium iodide then falls off, and that is going to be good for the reaction. So those are small, good, powerful nucleophiles that can also act as bases. On primary, they are still going to do SN2. So B would be small base plus good nucleophile. And on primary, they would do primarily SN2. So, and they don't do E1, SN1, even though they are in protic solvents, because the SN2 would happen a lot faster. Let's say we want only SN2. What can we do to push this even more towards SN2? SN2 is always a lot faster in aprotic. So if you have aprotic, it's going to be almost SN2. So let's say DMF or DMSO, so many other, ethers, all of these, THF, all of these can do SN2, okay? Let's look at what C group of bases can do. These are very strong bases. C group of bases, they're only bases. They're not going to do a backside kick if they can help it. They're just going to grab a proton and run. And where will they grab the proton? Always and only from the beta. And that too, it has to be aligned 180 degrees to the iodide. So let's say you have a hydrogen here, that it's going to go with the hydrogen. So the bases here that are only going to be bases are going to come in, and that's going to pull off the hydrogen on the beta, not gamma or delta. Another thing is if you have branching on the beta or the gamma, this being the alpha, the branching here would also really slow down SN2. But here it's not branch, it's fine. However, if you're branching on, let's say, beyond the third carbon, it doesn't really affect the rate as much because it's away from the active site. So branching on beta can really make a primary almost behave like a secondary. So you have to be mindful of that, and we'll do a branch primary later on. So it pulls off the hydrogen. The sigma bond here is rattled. Those electrons are looking to see where can I go, where can I escape from here, and they see here a very polarized bond. Iodine obviously is reaching to go, and it's a very polar bond. So you have a delta negative and a delta positive, and it sees more positive on this side. It's going to come running over here. And well, then it's going to have to kick somebody out because this carbon can only have 8, and obviously iodine's the only one. The Ci bond is weaker than the CH or the Cc, and so your hydrogens here really don't help much. These electrons then run with the iodine because the iodine wants to have a very nice octet. So then you have a pi bond that forms right here. And that would be the case for all of the big ones. So sodium hydride is really not used too much here to do an E2. Sodium hydride is used to deprotonate alcohols and so on. Hydrides typically do E2 more than SN2. Now this is not a reaction I've seen, but in general, this is what you would expect. If you want the iodide to be replaced by a H, then you would use lithium aluminum hydride. That's also another hydride. If you use lithium aluminum hydride, that is going to just make this into a alkane. If you take T-butoxide, huge base, it can do some SN2, but it also can do E2. And typically E2 is going to be more than SN2. And I'm going to draw the major product here, and that is going to be your alkene. Your minor product would be, and I put that over here, that is going to be a very minor product. DBU and DBN, if you look at the structure, you will understand why it cannot do an SN2. If you look at DBU, let's say it's got a 540. So that is going to be a nitrogen here, and then that lone pair comes down and kicks that pi bond, and that's going to do only an E2. If you attack with this to do an SN2, well, you're going to be stuck forever as a positive. It's not a possibility. So therefore, when you have DBU and DBN, DBN just has smaller rings, you can only do E2. There's no minor product as SN2, like even in the T-butoxide case. So you would have a double bond right here. E2, no SN2. And these typically come in very polar solvents, let's say DMF. All right, so we are done with C class. Let's go to D class. So let's spin that wheel. And let's start with our protic. Where is your nucleophile or your base? Nothing of that sort. It's almost like you forgot to put your most important guy. But you do have a weak base, weak nucleophile here. Let's see what it can do. This is a primary. If you ionize this, you're going to get a primary carbocation. And next door, you only have hydrogens. So really, you can't even have somebody jump over because that's only going to give you a secondary carbocation. And, you know, I mean, there can be a lot of scrambling around and you can get a lot of side products. Why would you even do this? You really typically don't. But sometimes if you have a whole bunch of side products on your NMR and you want to know how it came about, then you try to draw a mechanism for it with rearrangements. Okay, so in this case, SN1 is really very, very slow on primary. So therefore, SN2 is actually a little faster, even though this is a very weak nucleophile. Okay, so primary SN1 too slow. You would never take this and say, oh, let's do a nice SN1 to make this into an alcohol. Never, because you can just treat that with sodium hydroxide and get that done like this. SN2 is actually faster than SN1. Again, this is typically not by choice. And so your water will attack, displace that, get deprotonated by another water, and you can get very slow reactions, and this is really not an optimal way of making it, and you would get an alcohol eventually, and you could get lots of side products with rearrangements. Let's look at methanol. Methanol, you would expect about the same story. Water is a lot more ionizing than methanol. Dielectric constants like 80 for this. Methanol's like a lot, almost half of it. And so this would be even slower. So you could say over here, eventually you could get something like this if you have a, a little bit very slow. And for all of these, SN1 would be too slow, SN2 would be faster than SN1, and eventually you might get some of this, plus a whole bunch of side products. What about ammonia? That's a protic solvent, and it's neutral. What does that do? Well, this has got 2 lone pairs, this has got 1. Does that mean it's not going to do anything? Turns out ammonia is actually a very good nucleophile. It is a little bigger than oxygen because when you go from right to left on the periodic table, your size increases. So when your size increases, your nucleophilicity also increases because your electronegativity decreases. So this is a better nucleophile than oxygen, the nitrogen. So therefore, you are going to do an SN2. And you would get NH3 plus, and then the iodide is going to be there. Now you're in also a solvent that's basic, so it'll deprotonate that, and that NH2 with the R group is an even better nucleophile. That's going to come and do more SN2 here and deprotonate, and more SN2 deprotonating keeps going until all of those hydrogens have been deprotonated, and you would finally get a molecule where your nitrogen is holding on to 4 of this and becoming a positive, with an ammonium iodide, tetraalkyl ammonium iodide. So even though this is a protic solvent, it behaves differently because of the nucleophilicity. All right, so it's a good idea to study your reagents, see where they are on the periodic table, see if they're good nucleophiles, look at their sizes, charges, every single thing matters here. Whether it's going to be a base or a nucleophile, whether it's going to be just a base or is it going to be just a nucleophile, and if it's just a nucleophile, what are the things that you could do to push SN2 over anything else, like use aprotic solvents here. These are all really very important details. And if you watch the previous videos, I've gone through a lot of these reactions, one by one, like SN2, SN1, E1, and E2. We don't really talk much about E1. E1 here would be with the protic solvents. However, E1 is a very minor side product. Okay, so this is really very slow. E1 is going to be so minor. It's really not significant. Just to summarize, again, what we've done on our primary, let's look at all the 4 reagent groups and see if we can come up with trends. If you have a very nice, beautiful primary, unhindered primary with good nucleophiles, it's just going to be a very nice direct SN2. If you have aprotic, it's going to be even faster. If you have protic, it's going to be slower, but it will still take place. If you have a small base, and that's also a good nucleophile, because of the lack of steric here, SN2 will predominate. Therefore, you would have a backside attack and give more substitution than elimination. There may be a minor amount of elimination by pulling off the beta hydrogen, making a pi bond, and kicking out that leaving group. Now, for all of this, leaving group ability would play the same role in the rate, because for SN1, SN2, E1, and E2, the bond breaking here happens in the rate determining step. Therefore, the leaving group ability affects all of them. So having a good leaving group will increase the rate for all of the reactions. So lower the pKa, better the leaving group. Over here, when you go to strong bases or bulky bases, these typically do E2. Now, again, I was just going to mention sodium hydride is typically not used to do E2s. We use these. If you want to use a hydride to do a SN2, you would use lithium aluminum hydride. Now, over here, you have methanol, water. These are protic solvents. They don't have the muscle to kick out the iodine in one step or do an E2 one step. They are typically solvents, and they do hydrolysis or solvolysis. And these happen in multiple steps. And they are slower than their counterparts here. All right, we will come back. We will change the center, the axis or the axle of this wheel, and do another wheel for you. Until then, pam, pam, pam. See you soon. Bye.